Hi, in this video we look at an example where we need to do the sketch of the graph of a function that contains a parameter. In this case, we're actually not looking at a single function, but a family of functions that is obtained by considering different values of the parameter. The example is motivated by an optimization problem. Consider the following problem. A line segment of fixed length A is positioned so that its endpoints touch the positive side of the x and the y-axis as depicted on the following figure. Investigate the graph of the area of the triangle bounded by the axis and the line segment as a function of the x-coordinate of the endpoint of the line segment that lies on the x-axis. The figure below illustrates the problem. In bold, we see the line segment of length A whose endpoints touches both axes. In light blue is the area of the triangle bounded by the axis and the line segment. By varying x, we can change the triangle and its area. Therefore, the area of the triangle is a function of x. The goal of this exercise is to sketch this function and see how it depends on the length A of the line segment. A is what we call a parameter for this function. So informally, a parameter is a constant of an unknown value. It is possible that the graph of the area and its maximum will depend upon the value of the parameter. To define the area function, we recall that the area of a triangle is base times height divided by 2. Here the base as length x. The hypotenuse is the length of the line segment, so A, and the height, call it h, satisfies the Pythagorean equality x squared plus h squared equals a squared. Therefore, h squared is a squared minus x squared, and h is the square root of a squared minus x squared. Hence the area A of x is base, so ax, times the height, h, divided by 2, so x times the square root of a squared minus x squared, divided by 2. So it is this function a of x that we want to graph, and notice that it depends on the value of the constant a. For different values of a, we get a different graph of the function. So by varying a, we will be graphing not just one function, but an entire family of functions. To graph the function, we investigate the domain of the function, its continuity, its derivatives to see where the function is increasing, decreasing, concave up, and concave down. So now we start with the domain. The domain are the possible values of x. Now since x lies on the positive side of the x-axis, then x is non-negative. But since x can not be longer than the length of the line segment, then x is less or equal to a. The domain is therefore the closed interval 0a. We quickly notice that this function is the product and composition of continuous functions, polynomials, and square root functions, so it is continuous on its domain. So to graph this family of functions, we can go on the website geogebra.org. And GeoGebra is a free software that will do plenty of things, but for right now what we want to do is graph a function and maybe vary the value of the parameter. So I'm going to click on the graphing calculator here. It takes me to this page, and I have basically here the possibilities of entering the function that I want to graph, but this function depends on a, so I'm going to go in Tools and select a slider that will allow me to actually have a slider that will vary the value of the parameter. It's already called a. I could change the name here if I wanted to. And then I can set up the min and the max values. The min value I want it to be 0, and say the max value for the parameter I'll fix it to a, and I'll click OK. So I have my slider here, so as you can see I can move it around and change its value. I'm going to go back to to algebra, and I'm going to type the function that I want to graph. So I type just a of x equals, it's a function. I could enter directly the expression for the function, but I also want to specify the domain of the function. So this is why I'm using function. So I'm going to type x times the square root of, so this is where I can use the value of the parameter, because it's going to know what it's like, because I've defined a as 3.08 here, so that's what the current value of a is in the expression. So I subtract x squared, and we're going to say that the variable is x, and that we want to graph the function from 0 to a, because that's the domain of the function. As you can see, it's already displayed on the Cartesian plane. So I'm just going to type. I don't think did I type enter? Okay. Oh, I need to type enter. Okay. All right. It's working. So you see, as I vary a, I can see what my family of functions look like. In particular, I can see that globally it always looks the same. So it's always increasing and then decreasing. It reaches a maximum somewhere. It's graphed from 0 to a. So as you can see, the current value of a is 3.3, and that's how far we're graphing this function. And I actually noticed that the area is 0 at 0 and at a, as expected. And somewhere, it's not really in the middle, but somewhere within the interval, there's a maximum. And as I change the value of a, I can see that the maximum is changing, but relatively speaking, compared to a, it seems to be always located in the same place. Okay, so this is something we should expect to see when we're gonna find out what are the coordinates of the maximum vertex of this curve. So okay, let's go back and see if we can figure out the different derivatives of a in order to properly understand where that maximum is, and maybe prove that the function is always concave down, increasing first and then decreasing afterwards. So those are all the type of things that we want to do when we investigate the graph of a function or a family of a function. To confirm what we have observed in GeoGebra, we will now study the function a and its first two derivatives, and study the sign of these functions on the interval 0a. Now, to study the sign of a function, we must find where it is equal to 0 or undefined. Let's start with a. We have a of x equals 0 if and only if x is 0, or a squared minus x squared is 0. The second equality is true if x squared is equal to a squared, or if x is plus or minus a. But we only keep the roots that are within the domain of a. So in the interval 0a, a of x is 0 when x is 0 or x is a. Note that this makes a lot of sense, since when x is 0 or x equals to a, their area is 0, since there is no triangle in this case, but merely a line segment, or if you prefer, the triangle is completely flat. To study the sign of a, we investigate how the sign changes between the zeros of the function, or where it is undefined. Here it is defined everywhere, so that is not an issue, and the zeros turn out to be the bounds of the interval. Therefore, the function has the same sign within the open interval 0a. It's either entirely positive or entirely negative. Because x is positive on the interval and the square root is also positive, then the function a of x is positive within the interval, and its graph lies above the x-axis. We indicate this information on a real line, where values below the line are values of x, and values above the line are values of a of x. For example, at 0 and a, the values of the area are both 0. In between, the area is positive, and we indicate this with a plus sign. The next step is to investigate the sign of the first two derivatives. This will tell us about the increasingness, decreasingness, and the concavity of the function. Now, as an exercise, compute on your own a prime of x and a prime prime of x, and see if you can get the expressions given here. So now, pause the video and differentiate the area function twice. To differentiate a of x, we factor 1/2 outside the differential operator and write the square root as a power function to better differentiate. Then we apply the product rule using the chain rule to differentiate the second factor. Then we write our answer without negative powers, since these indicate that we have fractions. We write everything over a common denominator, and finally group like terms in the numerator. We could still factor the numerator, but we prefer to stop here. To differentiate a of x a second time, we use the quotient rule, using the chain rule once again to differentiate the denominator. We write our answer without negative powers, and we see that in the numerator there's a fraction. In order to write our answer as a simple fraction, we write the difference in the numerator over a common denominator. This common denominator is square root of a squared minus x squared, and when it multiplies square root of a squared minus x squared once again in the first term, this term becomes minus 4x times the square of the square root of a squared minus x squared, so minus 4x times a squared minus x squared. Then dividing by a squared minus x squared is the same as multiplying by its reciprocal, which explains the 1 over a squared minus x squared. Next, we expand the numerator and multiply in the denominator the 2 powers of a squared minus x squared to get a squared minus x squared to the 3/2. Then we group like terms and factor a common factor of x. Finally, multiplying by a 1/2 is the same as dividing by 2, and we get our final expression for the second derivative. The two derivatives found are displayed here. Notice that on the open interval 0a, the denominator for both functions is positive because x is less than a. And in that case, x squared is less than a squared. Therefore, the sign of a prime and a prime prime only depend on the sign of their numerator. Furthermore, they are both undefined at x equals a, since this creates a division by 0. So to study the sign of each derivative, we must set them equal to 0 to find their zeros. Now a prime of x is equal to 0 when its numerator, highlighted in red, a squared minus 2x squared, is equal to 0. This means that 2x squared is equal to a squared, or x squared is a squared over 2, or x is plus or minus a over square root of 2. But only x equals a over root of 2 lies in the interval. A prime prime of x is equal to 0 when its numerator is 0. It contains two factors, x in red, and minus 3a squared plus 2x squared in green. Hence, when one of these is 0, the second derivative is 0 as well. So when x is 0, or minus 3a squared plus 2x squared is 0, this makes the second derivative 0. Solving for x gives x equals 0, or x is plus or minus the square root of 3/2 times a. When we only keep the solutions in the interval and root of 3/2 times a is larger than a, so therefore the only 0 that we keep is x equals 0. We've prepared the sign charts indicating the values of x when a prime and a prime prime are either undefined, so that's at x equals a, or equal to 0. In between, this is where the function can change sign. So to study the sign, we choose test values, or we investigate the sign of each factor. So here in this video, we choose to investigate the sign of each factor. Recall that both denominators of each function is positive within the interval, so we only need to worry about the sign of the numerators. Starting with a prime, we need to investigate the sign of the function on the interval 0, a over root of 2. The sign of a prime depends on the sign of a squared minus 2x squared. So when x is positive, but less than a over root of 2, then x is less than a over root of 2, which is equivalent to x squared being less than a squared over 2, which is equivalent to 2x squared less than a squared, or just a squared minus 2x squared larger than 0. Therefore, the numerator is positive, and a prime is positive when x is less than a over root of 2. Similarly, it is negative when x is larger than a over root of 2. So adding this information on the sign chart, we see that before a over root of 2, a is increasing. So we indicate this with an upward arrow, and decreasing afterwards, and we add a downward arrow. Notice that the plus and minus on the sign chart refer to the behavior of a prime, but the arrow to the behavior of a. The sign of a prime prime also depends only on its numerator. Because a prime prime is defined and has no roots within the interval, its sign is either entirely positive or entirely negative. So this means that the function is either concave up or concave down, but not both. Now in the numerator, the first factor x is clearly positive, and the second factor, minus 3a squared plus 2x squared, is less than minus 3a squared plus 2a squared, because a is the largest possible value for x in the interval. But minus 3a squared plus 2a squared is minus a squared, which is negative. Therefore, the second term is negative. So looking back at a prime prime, it is a positive times a negative divided by a positive. So overall, it is negative. This means that the function is concave down within the interval. We add this information to our sign chart and indicate with a concave down curve the behavior of the function a. To summarize our findings, we have included here all three sign charts, and with this we're now ready to sketch the curve. Notice that this is a concave down curve with a global maximum at x equals a over root of 2. We have also included the function value at the maximum in the sign chart of a, and this is explained on the following slide. When x is a over root of 2, so this is where the maximum is reached, the height h is root of a squared minus x squared, which is root of a squared minus a squared over 2, or root of a squared over 2, or simply a over root of 2. So therefore, the base and the height are the same at the maximum, and the triangle in that case is just half a square. So the area is base times height over 2, so a divided by root of 2 times a divided by root of 2 divided by 2, and this gives a squared over 4. The figure illustrates the graph of the function a of x with its maximum in a over root of 2 a squared over 4. And as we vary a, we can vary the graph of the function. Its main features remain, but the maximum and the domain change values as a changes. So this graph confirms what we had seen in GeoGebra in the first place, merely that the graph is always concave down and that it has a maximum. Now the maximum is at a over root 2, or if you prefer, 1 over root 2 times a, and 1 over root 2 is roughly 0.7 or 70%. So the maximum is roughly at 70% of the length of the interval, and that explains why the maximum is located slightly to the right of the midpoint of the interval. In the next figure, we see the triangle that has the largest possible area, which is a squared over 4, and this triangle, as explained, is the one that has the base and the height of the same length. In this case, they are both equal to a over root 2. Thanks for watching.